Welcome everyone. I'm Nicolai Parlog, or as I should probably say, I'm Nicolai Parlog. So my dad is from Romania actually, so he's from around Brela. And I've been to Romania lots and lots of times, specifically in my youth. But this is the first time I've been speaking at conferences for half a decade now, but it's the first time I actually make it to Romania to speak at a conference. And I'm really, really happy to be here, to finally be at Vox Days Bucharest, and to talk to you about all the cool things in Java. Okay, so as I said, I'm Nicolai, and today it's going to be you, me, and data-oriented programming in Java. Well, 20 says the program, but that was like the day before yesterday, so that's already old news and boring, so we're going to talk about Java 21 instead. But you know, the differences are minor. I'll point it out when we get there. So, I'm first going to give you a very, very short introduction to what data-oriented programming is. It's not going to tell you anything, so then we're going to go through a lengthy example, which I'll use to introduce all the new features that work together to unlock this new, or at least new to Java programming model. And then in the end, we're going to give it a short review. I invite you, I could probably increase this a bit, right? I think this is better. Right, I invite you to go to slides.nipafx.dev, and on the right-hand side, you will see a link to this slide deck. So you can see it there, and you can follow along. There are links in the slide deck that you can then use. So give that a go. I'll show the URL later. Okay, so as I promised, let's start with what data-oriented programming even is. Before we get to that, we have to talk about programming paradigms in general, at least briefly. So all of them, most of them come with an everything is a sentence, right? Everything is a function, everything is an object. And what they're there for is to manage complexity. That's the main goal. We saw the keynote earlier where it was about simplicity, and of course the opposite of that is complexity. We're trying to manage that. And every program paradigm has different strengths. Some kinds of complexity they handle well, other kinds of complexity they don't handle that well. And that's why there is no universal best programming paradigm. That's why the answer is always it depends, and if you're asking somebody who knows what they're talking about, they will try to tell you it depends on what specifically. So what does it depend on, whether function programming or object-oriented programming or data-oriented programming works better? So object-oriented programming, of course, comes with an everything is an object sentence. That's the big message of object-oriented programming. It combines state and behavior in the classes that we write day in, day out, right? We have fields, we have methods on that. Often we have mutable fields, so the state evolves over time. It hinges on encapsulation on the class level, on the package level, on the module level, on the application level. The idea is to create smaller and smaller sub-problems and then then solve them in this smaller space. And if we talk about polymorphism, meaning the behavior that differentiates, then we usually do this by inheritance. So we have the collection, for example, the collection interface has an add method, and then ArrayList implements add, and hashset implements add, but obviously totally different ways because they have different data structures. So that's how polymorphism is implemented here. And it works best when we're upholding or defining boundaries. That could be boundaries between a client and a user of a library, sorry, a client and an implementer of a library, or it could be across different versions. It could be security boundaries. There's tons of different boundaries, and object-oriented programming excels in defining and upholding these boundaries. So, as I said, great use cases for that are when it is about boundaries, and that makes it particularly useful for large programs, right? If you have a large program or problem to solve, then if it's a large program, you could use object-oriented programming. If it's a large problem, you don't use object-oriented programming to create microservice, obviously, like a microservice architecture, but you use the same approach. You're trying to find different parts of the problem that only connect with other subsystems in defined ways, and then you solve those silos. And if you start to go into one app or one system, then you will usually, if you use Java, for example, use object-oriented programming to split that up into smaller and smaller problems, so you can solve each of them individually. But if you come down to a certain size, at some point that not stops being useful, but it stops having all this power that it unfolds on a larger scale. The smaller the problem gets, the less need you have for boundaries. Because if you have like 2 million lines of code in a code base, you definitely need boundaries to understand them. But if you have 20 lines of code in a class, you can make do with fewer boundaries. And if you have systems that focus a lot on data, where it's a lot about just taking data in, maybe like an event stream in JSON, manipulating it a little bit, and then maybe dumping it to a database or sending it to a different service. If you have something that's very strongly focused on data, that's also a place where object-oriented programming doesn't shine that much because it doesn't really have a good distinction or definition of what data is. Everything is a usually mutable instance of a class. And this is where data-oriented programming comes in. None of what I'm telling you today is my own thoughts or my own ideas. That all comes from Brian Getz's seminal article, Data-Oriented Programming in Java. I even stole the title, basically. Brian Getz is working on Project Amber and Project Valhalla. He's working for Oracle. He's very active in the OpenJDK community. He's the, I think, Java language architect, I think is the official title. So, you know, he thinks a lot about what Java could look like in the future. And I really invite you to read that article. And in that article, he finds some guiding principles. I'm not super happy with those because I don't think they're orthogonal enough, but I didn't dare talk to him about it yet. So the guiding principles are model the data, the whole data, and nothing but the data. Data is immutable, it's a core property. Validate everything at the boundary to make sure you do not have any illegal states in your system by making them unrepresentable. And so those are just like some 4 guidelines that probably don't mean a whole lot to you. So what I want to do now is, I want to get to that lengthy example that I mentioned earlier. And now I'm going to introduce the example to you, and then I'm going to show you a possible object-oriented solution that is intentionally full of flaws. And then we're going to see how a data-oriented approach could solve the same problem, from my perspective, in a better way. Okay, so let's start. What's the example about? It's a little GitHub crawler. You start with a seed URL, and it will connect to the URL, identify what kind of page it is. Could be a pull request page, could be an issue page. Then it looks for the interesting section, which is not the header and not the footer and all that stuff, but just like the part in the middle, the conversation on an issue maybe, and identifies all outgoing links. And then it takes all of those links and puts them back into step 1. If it finds an external page, you know, somebody links to Wikipedia, it talks to that page and fetches that, but then it stops investigating it. And there could, of course, be errors, right? Some of those links might be dead. And it's probably useful, although not mentioned here, to limit that at a certain depth. Otherwise, we're going to crawl all of GitHub, which is probably not a good idea. Right, so that's the program. And all of that behavior that I just told you, all of that happens in that method load page tree, which we're not going to look at. It doesn't matter to us. It somehow does this thing, right? It uses the HTTP2 API that was added in JDK 11. I have an implementation that even uses virtual threads. So it does all of that, but what it spits out is an instance of page, which is the top page that we started it, and then all the pages that are connected to it. And now the question is, what does page look like? We have a bunch of requirements. Every page has a URL. If the page was not resolved, it has an error. If it was resolved, it has some kind of content. And if it turned out to be a GitHub page, it has a collection of outgoing links and has an issue number or pull request number. We're going to pretend for a second that GitHub has only those 2 kinds of pages. Right, so that's the requirement for the page. And then we also have some operations working on that. I could have come up with more complex operations, but they have the disadvantage to not fit on the slides very well. So I came up with 2 very simple operations, which is we want to pretty print the whole page tree, and we want to evaluate some statistics. Right, so we have this state basically that's defined here, or required here, and then we have the requirements for the operations here. So what could be a possible super simple object-oriented approach? Well, we create a page class that has a bunch of fields and has a bunch of accessors for those fields. You will notice that they don't say get URL and get error. I stopped using the get word, like, I don't know, half a decade ago, because it feels like cargo cult object-oriented programming, like every method needs to be a verb. So we say get URL, but really it is the URL, right? So, but anyway, like if you prefer, you could also imagine this to say get URL and get error and get content and all the like. Right, so this is basically just the state, the basic getters, accessors, and at the bottom there I have the 2 operations that I want to call on those. If I were limited to object-oriented programming, even then I probably wouldn't do it quite like that, because this solution has a bunch of shortcomings. The biggest one is that the type of page is implicit. I said earlier, we might have an error connecting to that page. We might have a GitHub page. We might have an external page. These types of pages are somehow present in that type that I showed you earlier, but it's hidden. It's not obvious which type of page I'm looking at. I basically have to know which combination of fields makes for a valid error page, or which combination of fields makes for a valid GitHub page. And that means The legal combination of fields is unclear. I can probably fix that with some good factory methods. But also the client that looks at that must define the type. So if I have a client that calls load page tree and gets back a page, they don't know what type of page it is. Now you can start also adding an enum, but that's not, I mean, that helps with that, but also makes the solution more complex. And I also have, in this specific example, disparate operations on the same class, meaning at the moment I'm concerned with pretty printing and evaluating statistics. Those are not terribly connected methods, and you can easily see if you create some essential domain types that are really central to your entire problem that you're modeling. Then there's often not a desire, but like there's often this impulse to make these classes very large, because then you need all kinds of operations on them. So let's say you write something that handles customers, and the customers need to, you need to send them invoices, and they need to be able to order something, and all of those very different methods, you could start implementing them all in the same class, which is not a great idea, right? Because then these classes grow too large. And this class already lays the groundwork for that. Okay, so let's take a step back from this. As I said, even for OOP, not optimal solution. And let's look what data-oriented programming is telling us. Model the data, the whole data, and nothing but the data. Okay, so the whole data is, we have 4 kinds of pages. Okay, so let's create 4 types, right? And creating 4 types is a bunch of code, so let's use records instead. Okay, if you don't know what records are, don't worry, we're gonna go through that. So records were finalized in Java 16, and the claim that they have is that they're transparent carriers for immutable data. The immutable part is important because it means all fields are final, but the more interesting part for us mostly is the transparent part. That means while a regular class says, yes, I want encapsulation, all my fields can be private and everything, a record says, I don't need encapsulation. The fields are still private, but there will always be accessors. And the advantage of that is that, or one advantage of that is that the compiler understands what a record actually looks like, what components it has, and how to take it apart and put it together again. And we'll see that on the rest of the talk. But the most obvious advantage is I don't need so much boilerplate. So if I create a record like this that says a record external page, and this is weird, right? So imagine it would say class here. Imagine this would say class. And it says external page, and then what is this? What is this thing in parentheses behind the class name? It looks a little bit like a constructor. And it kind of has some similarity in the sense that the constructor defines what arguments it takes, and this defines what components this record consists of. This record has the components URI, which is URI, which is the name URL, and then it has a content of type string. And because the compiler understands that, it can generate all kinds of stuff for us. It gives us 2 private final fields, so 1 private final field for each of those. It gives us a constructor that takes those arguments. It gives us accessors that are called URL and content. It gives us equals, hash code, 2 string implementations that use these 2 components, or these 2 fields. So this is a complete definition, right? This class is usable. If you write class external page and then curly brace open, curly brace close, it's useless. But if you write this, you can actually use it immediately. You have a constructor, you can put stuff in, you can get stuff back out, you can start working with it. And you can customize all the things that I just mentioned. What you cannot do is add additional components. You cannot add a field, for example, because the record is transparent, remember? So only the components up there are allowed as state. Okay, so let's do that. Let's use this to model the data. So we start with creating the error page, which has, when we look back at the requirements, a URL, and since it was an error page, it has the error, which in this case I picked an exception, but it could also be just the for reply, whatever. The external page has the URL again, and content, because apparently I caught the page, it could be a Wikipedia page, so I grabbed the HTML content, so I want to store that. And then I have the 2 specific examples of the GitHub issue page and the GitHub PR page. And they have more stuff. They have a URL, they have content. This is not formatted that great. So both of them have URL, both of them have content, both of them have a set of outgoing links, because, remember, I wanted to crawl all of GitHub, or, almost. So I want to store those links. Those are also pages, of course. But then the GitHub issue page has an issue number, and the GitHub PR page has a PR number. So far, so good. And as I mentioned, all of these types work like that out of the box. We can start using them immediately. Again, model the data, the whole data, and nothing but the data. We've missed something here. Yes, we modeled all the types for according to the situations that we have, but there's relations between them that we didn't model so far. These at the moment are 4 disparate types. They have nothing to do with one another. They're unrelated, but that's not really what the actual data is. The actual data tells us, look, when we load a page, it's either successful or not. There are only these 2 options. And if it was successful, it's either an external page or it's a GitHub page. And if it's a GitHub page, it's either an issue or pull request issue or pull request page. Once again, we're acting as if there were no additional pages on GitHub. Right, so these relationships between them, we have not modeled them, and these relationships very often are these kinds of alternatives. It's this or it's that. So let's have a look into that, how we can do that. And this is where we use sealed types. So okay, let's take a detour again. Let's look into what sealed types are. These were finalized in Java 17, so if you're in the latest LTS, you can use them. And what you do with them is you limit inheritance. You tell the compiler and your colleagues that only certain subtypes are allowed. And then your colleagues understand that they shouldn't randomly add subtypes, and the compiler can use this knowledge to check exhaustiveness. Now, put a pin in that. If you don't know what that means, that's not a problem. We're going to come to that later. Right, but that's important. We're communicating that the number of subtypes is limited. And how are we doing this? In this case, I created a sealed interface page, so we add the keyword sealed. And then what we also need to add, not always, but in most cases, is a permits clause, which says, okay, so this interface page is sealed and only permits these 2 subtypes. That means only error page and only successful page can implement or extend that interface. Every other type, like interface my page extends page, will not compile. The compiler will say, no, you said that page can only have these 2 subtypes. This one is not mentioned, so I will not let you do it. This just seems like more work. Why would I do that? We see the benefits of this later. But that's essential to this, to modeling these alternatives. And you can see where this is not a general solution, like it's not a general solution to all kinds of problems, right? For example, the collection interface doesn't need to be sealed. It's intentionally designed in a way that you can have tons of kinds of collections, lists and sets and all the implementations and queues. So of course, collection would not be sealed. You only do this when you want to limit the number of implementations that can be there. And you might want to do that because your system hinges on a certain amount of types that you have, and you know you cannot just randomly add some. So for example, if you added an additional kind of collection, then your code can probably work with that other collection if it's suitable, right? But let's say you create a rendering pipeline, and your rendering pipeline can render shapes. And let's say you start by rendering lines and triangles. Okay, that's great. Now, if I just add an implementation for circle, I will not expect the whole rendering pipeline to do all its things perfectly, right? It's not enough to add that type. You probably need to add a lot of code all over the place to make it properly render a shape. Or if you're writing something that deals with employees, for example, right? So you can invoice actual employees, or you can invoice contractors. If I add a third kind of person working there, your system might not automatically do all the right things. You might have to add code all over the place. So every time you're in a situation where you're realizing, I have this interface and I have these implementations, but I can't just randomly add another implementation and expect everything to just work out of the box, that might be a situation where sealed type better catches what the actual domain landscape tells you. Okay, but this specific case, we're picking the interface page and say, okay, it's either successful or a failed load. And then the implementing types, error page and successful page, they must have to fulfill some conditions. So they must be in the same module as page, or if you don't use modules, they must be in the same package even, which is even stricter requirement. They must directly inherit the sealed type, so you cannot put stuff in between and inherit from this type, and that type eventually inherits from page. And error page and successful page, they must make very clear how they deal with further inheritance. So they must be final, preventing other inheritance. They must be sealed to redo the same thing, or they must be explicitly declared as non-sealed, which says, from here on out, down there, I can have all kinds of implementations. It's just to make this very explicit. Okay, so let's do this. Already showed you the sealed interface. It will have a URL, right? Because the page interface, because every page has a URL, and then it was successful page load. It has content, and then a successful page load could be a GitHub page, or it could be an external page. And the GitHub page then comes with additional links, and I added this subtree method, which comes in handy later, which just streams all the pages in the subtree. So this is the hierarchy we're creating. I think that's how UML works. Blue are interfaces, orange are records. So we have these interfaces here. We have page here, as I mentioned before, and then we have either successful page or an error page, and that splits again, and that splits again. And that's the types we just created. The important part to understand is, looking at page, these are all the possible subtypes. There can be nothing else, because on every level, this is either final, all the records are final, or they're sealed themselves, all the interfaces are sealed. So if I have a page, I know it must be one of those types. It cannot be any other type. And I keep repeating that. As I said, it becomes important later. Okay, another important aspect of data-oriented programming is to make illegal states unrepresentable. Now, earlier, we had this mishmash of fields where a lot of combinations were not legal. We've already solved that, right? So for example, earlier we could have an instance of page in this object-oriented approach that had an error and a content. That made no sense, right? Where does the content come from if the connection erred out? So these combinations are already illegal, right? None of them work anymore because we used specific types to the specific instances of data that we can encounter. So that's a big step forward. We also need to validate the boundary. That's where we make other illegal states unrepresentable. We need to reject other stuff in constructors. So in this case, I have the record for external page here. And so that's the component. It's URL and string, right? And this down here is the constructor. Let's focus for a second on what the constructor does. It just says, I want the URL to be not null, I want the content to be not null and also not empty. Now, the constructor looks a bit weird. Like, why does it not mention the parameters? Well, since every record always has a constructor that takes both of these arguments, that's the called canonical constructor that always exists. And if I want to refer to it, I can leave out the components if I want to. So basically, this is then called the compact constructor, and you could imagine this just having the parentheses here with URI, URL, and string content. If you write it like this, the record first, then usually we add fields, but records cannot have fields. Then we usually add constructors, put this one at the top, then it's just like 2 lines from the compact constructor to the list of components. And the advantage is if you ever add a component, you don't need to touch the constructor unless you want to add something. It just removes a little bit of boilerplate. But you don't have to do this. Like, nothing is stopping you from listing the parameters here if you prefer. Okay, now data-oriented programming also said one of the guidelines, data is immutable. So records are already shallowly immutable, meaning the fields are final. You cannot reassign them, but the types that you put in there, they might not be immutable, right? So for example, the GitHub page has a set of links. That's a set of page. And a set can be mutable. So if you want to insist on immutability, which is a good default if you deal with records, you probably want to create immutable copies, for example, of collections. That's straightforward. The methods added in Java 9. So this one was added in Java 10, I think. Set.copyof takes a set and gives you back a copy of that set that is immutable. Now, if the things in that set are mutable, then that could be an issue as well, right? So like the immutability, like in Java, immutability is never possible to say, okay, from here on out, I have a field, and this field can have a collection, and this collection can have users, and users can have addresses. There's never a way in Java to say, okay, on the top level, I want to make all of that immutable. That never works in Java. In Java, you can always only make like the one thing immutable if you're lucky. Like you have a collection, you create an immutable copy of the collection. If your user class is mutable, there's no magic that you can employ to make the user immutable. You just have to deal with it. Anyway, okay, let's keep going. Where are we now? So we created a page type that is now, the page type is now explicit in the type system, in the types that we created. Only legal combinations of the fields that we want are even possible. And everything else, we made sure that it doesn't get past the constructors, meaning that, like empty content, for example, is not possible. I would say that the API is much more self-documenting now, because when you see that I get a page back, you can see, okay, the page can only have these subtypes, and the subtypes immediately tell you what they're about. They're an error page or GitHub page. It's very easy to see. And this code is much easier to test, because the code we started with actually had a lot of combinations that we might not want. We had to test those. Here, all you maybe have to test is whether what happens when you put an empty content or null into one of our in the successful page or something, right? But the records themselves, like there was basically no code there. So much of this code doesn't even need testing, because as we try to do when we use a type system, we try to express as many properties as possible in the type system so the compiler can find errors instead of putting them softly into code and then we have to write tests to verify them. Okay, that's all good. So the static situation now is we have all this data, we can now basically snapshot all the data we want to have. What about the operations? What about the behavior? Where did they go? Still part, and that's why I don't disagree with Brian, that these are like the best guidelines. Model the data, the whole data, nothing but the data, that says nothing about behavior. Intentionally, it's basically implicit therein that you don't want to put the behavior onto the data. You have the data here, and you put the behavior elsewhere. That's not entirely true, right? If you say to a page, give me a URL, you could argue that's behavior, hardly. But if you tell it to give you the host of the URL, I mean, it's still not really behavior, but it does a little bit more already. And if you just want to evaluate some statistics or return a string that is like, you know, a string that you can pretty print, you could argue that these are also basic derived quantities. You can just look at one page, you can just create this representation as a statistic or as a string. And so these are not really good operations to showcase this. Better operations are ones that deal with more complex domain objects, or maybe like some services that they need to pipe data into, everything that touches not just on the page, but also on other code. But again, I want to keep the example simple so they fit into the slides. So let's pretend for a second that these were not just simple derived quantities and we needed to do something a little bit smarter. Okay, so let's look into that. Pattern matching on CL types are perfect for this. So we have polymorphic data, meaning we have data that has different shapes, and we want to have operations that behave differently depending on their shape. In object orientation, we would usually use inheritance for that, right? So we'd have an interface that describes a method pretty print or whatever, and then would implement that on these classes. But as I said, we don't want to implement it on these classes. We want to implement it elsewhere. So we need to look into that. But since they're all records, and records don't care about encapsulation, we can access all the data we want. Because that, you know, usually we use encapsulation, and you want to do that so you can just have access to private data. But if you make the data non-private, you don't, like private state, right? But if you make the state non-private, every function from the outside can just access everything. Okay, so we start by, let's talk about type patterns first. These were finalized in Java 16. What are they? So what they do is they do a type check, a cast, and a declaration all in one. So if you look at this line of code and you stop reading after GitHub page, like if you stop reading at the border of this like green square, you know this already. That's an instance of check. You check at runtime, is this a GitHub page, yes or not? And if yes, what you would do is you would cast to GitHub page, because presumably you need that type, and then you would do stuff with it. A type pattern does these steps at once, so you don't have to declare, cast, or type check, declare, and cast. So there's 3 steps. It does that all in one. So you say if a root page is an instance of GitHub page, GH page, then you get a new variable, GH page, that is only visible in this if branch. So only in that if branch are you able to use GH page. The compiler makes sure of that. That's called flow scoping, and it's already something that was present in Java before. If you declare a variable that's uninitialized and you initialize it in an if, then the compiler knows that in the else branch it's not initialized. So this kind of analysis is already present. You already know it to some degree. And this is the same. There's an if check, and if it's true, you can use GH page, and if it's false, well, you can't. Okay, you can do some funny stuff with that, which I'm actually going to do later on the slides. You can decide yourself whether it's a good idea or not. But look what I did here. I inverted the check, right? So I said, if root page is an instance of GitHub page, GH page, but not that, if it's not an instance, that means in the if branch, I definitely cannot use GH page because it's definitely not a GitHub page. But then I return out of that if. So the only way to reach the line below, the comment at the bottom, the only way to get to that line is if it was a GitHub page after all. So I can use it there. So if you do like early returns, and I do, I like to check error statements at the top. You can actually do this and check if it's this, I exit the method. If it's that, I exit the method. And then in the remaining block, you can actually use the variable from up there. But I can understand if people would say that's somewhat unreadable. So then you just turn around and say, if root page is an instance of GitHub page, and then you put the code that was down here in there, and then all is good. Okay. Now, we talked about patterns. That's final in Java 16. What is in preview since Java 17, and we have a good chance to be final in Java 21, would be they can also use patterns in switches. So what we do here is we take this page object, and instead of writing instance of this page and then maybe else instance of that page, we just do a switch. And then here we say, okay, in case it's an external page, please define a variable that's called, that has the type external page and is called ext. And then in that branch on the right-hand side, I can then start using it. If you don't know the error syntax yet that was introduced in Java 14, this also works with the colon, right? If you like the old style syntax more, case external page ext colon blah blah blah, that works too. Right. So what happens here then is that the runtime takes the page instance and basically goes as usual in a switch statement, goes through all the cases, looks for the first one that matches, creates a new variable, maybe GitHub PR page, of type GitHub PR page named PR, and then executes that that branch there. And we can put that together, type patterns and pattern matching, to now operate on a page object by looking at its specific type. Okay, so let's say we do this here. We want to evaluate statistics, right? So the static method, you could call it a function if you'd want to, that's called evaluate, and gives back a stats object, and as input, it takes a page. So what does it do? This one creates a statistician because we need to run some state, we need to increase some numbers, so I created a statistician to hold the state, and then I call evaluate tree on that thing, and then I return the result. And evaluate tree, that's the method below, that does this little trick, because if the root page is not a GitHub page, like it doesn't have children at that point, right? Only the GitHub page has links to outgoing pages. So if it's like, if the root page was not even a GitHub link, but like a Wikipedia page, it's just a single page. For that special case, we always have to special case that here in this code. It's not terribly important to what I want to show you. The important part is, what you get is, I eventually take the subtree of the GitHub page, and for each element in this subtree, I evaluate that individual page. And that's what this code does. It takes a page, and this is the polymorphic behavior. This is the behavior that is different by types. If you would be writing this as a method on page, you would probably pass in the statistician, so that then the page object could say, oh, I'm an error page, so I'm going to increase the error page count. And here we do it the other way around. So we are inside the statistician, we get the page, and now we have to differentiate by type. And this works, right? We got all the types covered. I used the double underscore here. This is no special syntax. I just use that because I don't need the type. Like I don't care I don't need the variable. I don't care about that variable specifically. If it's an error page, I know I need to increase the number of errors. If it's an external page, I need to increase the number of external pages. So the double underscore there, I'm just using that to basically signal to myself, it's a throwaway variable, I don't need that. Why it's a double underscore, you'll see that later. Okay, now let's go to the class pretty, which is in charge of printing a page list. It works very similarly. Once again, it's a static method that gets the root page, and then it makes this distinction, is the root page actually a GitHub page? And if it's not, then we just create this page name for the single page. But if it is, then we go through the entire subtree, create a name for each of the individual pages, and then we put those together with new line characters to create, a list of these things. So again, the important part happens in create page name. And this looks similar to what we've seen before, right? So we once again switch over the page type, but what we do differently here is we do not change some state. Instead, we return a result. We compute a result and return it, which if you do this like, functional leaning kind of programming is something that feels better. So what we're doing is we're saying, okay, return, coming back to Sander's talk from this morning, start with a return. We're returning the result of the switch, and if it's an error page, then the result is this fun little emoji, the text error, and then I get the error variable that I just declared here, and access the URL and get the host. And for the external page, I do the same thing. And the URL was already available on the page interface, if you remember. So none of this is yet terribly impressive. The important part starts here, where I'm going to talk about issue and pull request number, because now it really becomes important that if it's a GitHub issue page, I can actually access the issue page API. Namely, I can ask for the issue number, and the same for the pull request number. So this switch allows us to differentiate by type, and then use the API of the specific types to create the results that we need. And we can simplify that a lot with record and deconstruction patterns. And we're going to go over that next, but it doesn't fundamentally change what's going on. So if there's any, like one slide that's the most important of the talk, I would be saying it's this one, because it shows you how you can create polymorphic behavior in a function that is unrelated to these types. Okay, so let's look at record and deconstruction patterns. Record patterns were previewed since Java 19, so they just had their second preview starting yesterday, and the hope is that not much has to change, and if that is the case, then we can have a good chance that we finalize in Java 21 as well. So there's a JEP link that discusses that. And what record patterns allow you to do, they hinge on the transparency of records. Remember, classes use encapsulation, they hide their internal state, but records don't. So that means you can freely take them apart and put them back together. And record patterns allow you to do that. So you can deconstruct them in an if and a switch. So let's say if you have this external page here, this record, as I was defined earlier. And also what you could do is you have an object from somewhere. And then what we did previously was we checked, okay, wait a moment, not so easy to actually use this thing. If it's an instance of external page, and that's where we stopped earlier, right? We declared a variable for external page. What we're doing now is we're taking this further apart. We're saying, is it an instance of external page? And if it is, take it apart and declare one variable called URL for the URL, and another variable called content for the content. So instead of, if it's an instance of external page, I need to cast it and then take it apart, or with what we learned earlier, if it's an instance of external page, the type pattern gives me a variable of that, but I still have to call the accessors. I can, with records, because they are transparent, take them apart immediately on the same line. Just like if it's an external page, give me the content. And the same works in a switch. So we can start using that. So this is not the complete switch, because this gets actually a little bit longer now. So what we're doing here is we're taking the error page apart into its URL and the exception, and then I'm using the URL here. And I'm going to do the same with the issue page, and the same with the other two. As I said, for brevity, I've removed them here. But you get the point. It's a bit annoying, though, that I take the GitHub issue page apart into 4 components and only use the one. And I still have to list all the other 3. And this is where unnamed patterns come in. They are currently a JEP that is not yet targeted to 21, so it might not show up in 21. And even if it would just be a preview. So this is a little bit more off, but it includes more than this. It's very interesting, JEP. I'm really looking forward to that. But what it, at the moment, proposes is that in one of these record patterns, you can just use a single underscore here to say, I don't care about that variable. I don't care about its type. I don't care about its name. I'm never going to reference it. So who noticed the single underscore change in Java 8 and Java 9? Did anybody notice that? So up to Java 7, you could use a single underscore as a variable name. And in Java 8, that was deprecated. And in Java 9, that was disallowed. And when the deprecation happened in Java 8, I was like, I've never done that before, but why is it deprecated now? So I read up on it, and it said, well, you know, maybe in the future, we want to use it to mark that this variable is not used. I'm like, holy crap, I need that all the time. Like, you often create lambdas that take 2 parameters, but I only need the first one, I only need the second one. I always have these like additional parameters flying around that I don't want. I can't use the underscore anymore now. So I started using 2 underscores. That's why I did that on the previous slide. But hopefully when this lands, we can use a single underscore to signal, and also then we don't need to type anymore, right? Either. So you can signal, nope, I don't care about this, which makes this much more succinct, but more importantly, it makes it easier to read what matters and what doesn't. And you can immediately see if it's a GitHub issue page, I only care about the issue number, and on the next line, I'm immediately using that. And with that, together, the switch looks like this now. So now it's, as I said, it's the same thing as before. It's not fundamentally different, but it uses record patterns for deconstruction and the underscore, which makes all of these, what would usually be right-hand sides, if the slides would be wider, more readable. And even if you read just the left-hand side, it tells you more what's important, what are we caring about here. It better expresses what we want. Okay, now, this looks all great, right? But anybody felt a little shiver down the neck when I started doing instance of checks? Yes, that's bad, right? We're not supposed to do that. Why are we not supposed to do that? We all know, right? We're not, like, I never did this, and it felt really wrong the first times you do. It doesn't scale well in the future, exactly, because what happens when you add a new type, right? You have, like, if it's this type to this, if it's that type to that, add a third type, what happens now? I don't know, maybe there's an else branch, maybe it just falls to the method. It's basically undefined, and that's not great. Okay, so let's see what happens here. So we're now extending the operations. We're now adding a different type of data. We're saying, okay, we have a GitHub commit page. That was we newly discovered, holy crap, GitHub has commit pages too, we need those as well. So we create this type, this record. Makes perfect sense. There's a URL, we want to capture the commit hash, we have the content of the page and the page links as before, it implements the GitHub page, it's all great. Except we get a compile error, remember? Because GitHub page was actually sealed. So the compiler will tell us, no, 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 you can't do this. This is not a legal subtype. It's like, okay, let's follow those compile errors. So the first stop is the sealed supertype. So we go to GitHub page and say, okay, GitHub page now also needs to allow GitHub commit page, right? And this is where it all blows up. Everywhere you did a switch, where you did not use a default branch, I didn't talk about that yet, but you might have noticed that I didn't use a default branch anywhere. Everywhere we used the switch without default branch, they all have compile errors now. Because here's what happened in the past. The compiler knew that page is an instance of page, and it knows that once you've covered those 4 types, you've covered all possible leaves in this tree, right? Because everything between was an interface, so you cannot create instances of that, because you cannot create, for example, anonymous instances of a sealed interface. So once you've covered all those 4, you're good. You covered all possible implementations. And that's why all of those past pieces of code worked. Now if I add a 5th one, the compiler says, nope, you're not covering all cases anymore. And I'm getting a compile error here. So every operation that I created that is across all types now gets a compile error. Even though it has the term error in it, it's a good thing, right? Because it leads me to all the places that I need to update. This is exactly what I want. It's like adding a method to an interface and then going through all the types to add that operation. Although you might have already noticed that it's slightly different, because if you add a method to an interface, you go across all the types to make a change, whereas here, it's adding a new type that makes you go across all operations. I'll mention that a little bit later. Okay, so now I just add the 5th type, and I'm happy again, and all is good. But that means, to make sure that they're, I would say, maintainable or scalable, as I mentioned earlier, this only works well if you switch over sealed types, if you enumerate all possible types, even if some of them you don't care about, even if you say, like, look, I don't want to print the error page, still make a case for the error page that returns an empty string or null or whatever, right? So, not null probably. Put something in that so you don't need a default branch. Avoid those like the pest, because then you will always get these compiler errors when you add a new operation, and that's essential here. Okay, so once again, where are we? We have the operations separate from the data. Adding a new operation is easy. You just create a new long switch and do everything implementation there. But if you add a new type, you have to do a little bit more work, because you had a new type, and then you have to go across all the different operations and update them. And that's what I meant when I said earlier that this is like the flip side of object-oriented programming, because that's the other way around. Adding a new type means, well, you implement that interface. You just sit down and implement all the operations of the interface. But if you add a new operation, then you need to go across all implementations and add the method everywhere. So it's the dual problem of the other one. And that's also when I mentioned earlier that different programming paradigms handle different kinds of complexity differently well. This is a very simple but easy to understand example, where if you're constantly adding operations, this is easier. If you're constantly adding types, probably the other one is easier. Easier does not mean better, but it's different. Okay, good. That was the core. That's what I really needed to show you. Now we can relax and go a little bit over some odds and ends, and then we'll be done. Okay, so talking about relaxation, algebraic data types. If you're interested in that term, look it up, but I'm not going to go into detail here. It's not at all because I don't understand those. But records are product types and sealed types are sum types. If you want to know what that means, that much I can explain to you. Find me after the talk or at the conference. I'll be here today and tomorrow. But for now, I want to skip this. But it is a powerful concept. It's a concept on which many functional programming concepts hinge, and they use that a lot. So product types and sum types together, algebraic data types, are a good thing that Java has those now. Where would you use those? Specifically what I just showed you, where would you use the types as we just defined them? I would generally say there are like 3 good places to do that. One is ad hoc data structures, another is complex return types, and the last one is complex domains. For ad hoc return types, or like ad hoc types in general, we often have these local throwaway types that we just need like a little bit. Every time you think like, ah, damn it, why does Java not have a pair? I need a pair. No, you don't need a pair, because a pair is just, it's a useless name. Like the type tells you it's 2 things, great. What you can do with a record is, you can create a one-liner that says, this is the page with links. I needed that type actually, because there was a phase where I need the links to be mutable, because I was still gathering new pages. I want to add that to the set. Oh, sorry, just the URLs actually. And so I want to make sure that it's always mutable. So I create this intermediate type that I just used locally within a class. This is only not a one-liner because I went out of my way to add additional functionality. Like, I didn't have to do this. This class is used within one type. It's not even necessary to do this, strictly speaking. So if you ever have the feeling like, I just need something simple to combine these 2 data points in a stream pipeline maybe, create a record. It's probably a one-liner, and it's like a pair, but you don't have to deal with generics, and it actually tells you by name what it's about, which is a big step up, right? So yes, that's one great use case for those. The other one is for more complex return types. Think of something like optional. Optional is not that complex, but you could implement optional this way. Now that ship has sailed, but let's implement something else this way. Let's start at the very bottom, and I know not everybody can see that well, but we have a method here that wants to find a user by username and returns a match of user. And match of user is a sealed interface, and that says, well, look, I have these 3 possible implementation. Either I found nothing, I found an exact match, or I found some fuzzy matches. Some like, not exact, but you know, some people had similar names. So once again, we go there and we create this sealed hierarchy. We use records for the specific types that we need, and then we can use it as a return type, and often these are deconstructed very quickly. Often like optional, right? You make a request, you get back an optional. You might call map a little bit, but sooner or later you're done with optional. And this is something similar. You often deconstruct it immediately on call. So in this example, what I could do, is I could say, okay, look, I tried to find the user John Doe, and I switch over the result, and then I do 3 cases: case none, case exact, case fuzzies, and I do whatever. And this is what I mean when I say this is a very self-documenting API. Like, this is great. You see, I want to find the user, what can I get back? And the types tell you what you can get back. There's no need for like excessive Java doc explaining, well, you get a result object, and the result object can somehow be in this state or in that state. No, just get one of these 3 types, you switch over them, and you're done. Not the absence of the default, of course. Or you can use this for more complex domain, for long-living domain objects, as we just done. The page object that we just went through, they live through the entirety of this little crawler that I built. So I think these are like 3 places where you can use this, and you would usually start with more local or more limited types, and then once you get your feel around, maybe start to incorporate them in your domain. Now, who thought about, isn't this functional programming, this entire talk? Okay, a few. Isn't this basically that? Yeah, a bit. It's not quite the same though. So functional programming says everything is a function. You focus on creating and composing functions that operate on data. In data-oriented programming, you model data as data and write the functions that operate on them. So that will lead you to very similar situations in many cases, I will presume, because I've not used either of those extensively, but that makes sense, right? But the focus is on something else. There are often trade-offs in any kind of programming. So sometimes in a situation where you have to go one way or the other. And functional programming will tell you to focus on the reusability and composability of functions, whereas data-oriented programming will tell you stay close to the shape of the data in real life and then write your functions accordingly. But they're very close. Well, maybe not very, but they're close. Definitely way closer than object-oriented programming, because the next question is, does this kill object-oriented programming? Is it dead? Is it finally dead? No. I have to disappoint you, as I pointed out in the beginning. It's still a great approach to modularize larger problems and to start on a high level to turn that into smaller parts that you can then solve individually. But if you come down to a small enough scale, or to a place where like you're basically just streaming data back and forth, you really don't want to do that much. You don't need like behavior, you don't need changing state. You just want to take the data and write an operation on it. This is where I would recommend to consider data-oriented programming. And data-oriented programming is basically a summary of what we've done so far, hinges on Java's strong typing to model data as data. So we're not just using bags of data, we want to have this in a way that we're used to using them in Java, with like compiler safety and everything. So we want to model data as data with records, we want to model alternatives with sealed types. We use methods, probably static methods somewhere elsewhere, to model the behavior, and we make sure that we have exhaustive switches without a default branch, and we use pattern matching to deconstruct data quickly and easily so this code stays readable. And then we also don't have the maintainability problem that if we add new types, we follow the compiler errors. Once again, I leave you with the guiding principles. I'm not going to read you again, but data-oriented programming in Java, the article by Brian Getz, if this was interesting to you, I highly recommend giving that a read. And with that, I want to thank you very much for your attention.